Hi everyone, and welcome to Jimmy's talk, RAGtime with Postgres. Jimmy Angelakos, I hope I pronounced your name correctly. Please.
Yeah, that's right.
Okay, great. Now I feel better. Um, so he's staff software engineer of PGH, and I'm very excited about your talk, and I can't wait for it. So I'm not going to do some stupid blah blah blah, and I will just leave the word to you.
Thank you very much. So, I hope everyone can see my screen and hear me well. Um, this
I
is,
I confirm.
Thank you. So, this is RAGtime with Postgres, AI power with pgvector and Retrieval-Augmented Generation. Again, I've tried to break the world record for the longest presentation title and subtitle, and I'm very excited to be here. So, let's see. I don't know if you can hear the music that's playing. I'm not sure that is being shared, but I can hear a wonderful song by Scott Joplin, which is the Maple Leaf Rag. And Scott Joplin is known as the king of ragtime music. But in this talk, we're not going to talk, unfortunately, about the music genre. We're going to talk about RAG, which is Retrieval Augmented Generation. So let's see. First of all, I'd like to start with what is the hype around AI and what is the reality, because there seems to be a lot of noise in the field of AI today, and it's really hard to understand um, actually what the significant developments are, and also um, what is just simply marketing and hype. So, without further ado, we know all about the catchy, marketing speak and abbreviations like LLM, GPT, vector databases, AGI, the mythical AGI, for artificial general intelligence. We know MCP, basically an API. We know about LangChain, AI agents, agentic AI, which is not the same thing. So there are a lot of buzzwords in the field. But we in the database camp are also guilty of using buzzwords. So we have things like data lakes, we have data warehouses. I've even heard the term lake houses, which sounds like something you would like to spend the weekend at, serverless databases, and so on. So with all these buzzwords, it makes sense that people would be skeptical around the topic of combining AI with databases. And specifically for generative AI, as Professor Ulises Mejias of the State University of New York has said, one of the opinions is as we learn about how the technology works, and he means generative AI, we realize that it's nothing but statistically derived plagiarism, which is harsh, but if you consider how the dominant proprietary models have evolved by ingesting tons of copyrighted stuff, then you begin to see how it might not be a totally inaccurate statement. What is the answer to the hype? What is the answer to criticism like this? The answer is building practical tools. When you can use generative AI to build something that actually helps people in their day to day, then I think that is a very good response to the criticism. Now, let's talk a little bit about me. I'm making it clear I'm not an AI expert. I am a database expert, and specifically, I've been working with Postgres for a long time. I self-identify as a systems and database architect. I'm based in Edinburgh in Scotland. I've been using open source and trying to contribute back for the past 25 years. I've been using Postgres exclusively for the past 17 years for both personal projects and in my professional work. I'm a member of the PostgreSQL Europe Diversity Committee, and I've also written a couple of books, PostgreSQL Mistakes and How to Avoid Them, and co-authored the Postgres 16 Administration Cookbook. I've also written a Postgres extension called pgStatViz for the visualization and time series analysis of PostgreSQL internal statistics. Now, let's get into what we'll cover in this talk. We'll be looking at the what is Retrieval-Augmented Generation, why you should do it, how to do it, and also we'll solve one problem that I've selected with Retrieval-Augmented Generation, and we'll see how to build this solution. And we're also going to speak about tips of things that I stumbled across or stumbled on as I was building this solution. And finally, we're going to talk about some caveats, some things that can catch you out when you are building RAG tools. So first of all, let's start with what generative AI is. So Gen AI is primarily and fundamentally a statistical model. And we should all understand this, that it's a statistical model that produces as its output either text, pictures, video, audio, whatever. And it's what's known as a deep generative model in the sense that we use for deep learning. And why do we call it deep learning? Because it is trained on lots and lots of material to be able to statistically generate something from what it knows from its training material. So it makes sense that it's trained on a large corpus of data. In the case of some of the prominent models that people use, most of it is copyrighted, which the companies behind them are denying, but it has been proven that copyrighted material exists and can be returned by specific prompts. But moving past that, we'll look at what LLMs are. So LLMs are large language models. So they're basically a neural network for language-based tasks, which is we give them a text prompt and they return text. GPT is not actually a trademark. It is just an abbreviation that means generative pre-trained transformer, because these are models that output and they're classified as transformers. And that's what GPT stands for. It's generative. It's a generative statistical model that outputs text, video, audio, images, whatever it's been trained on. And that's what pre-trained stands for. It's already been trained. It has ingested all of the knowledge, in air quotes, that it is able to be trained on. So what is the problem with LLMs in general, not just current LLMs? So seriously now, LLMs can and do lie. In what sense? When they don't know the answer to your prompt, they just tend to make stuff up. Um, some people call this hallucination. Other people are less polite. This is the politest term I could find, but still it's problematic because it anthropomorphizes these models. They're not human intelligence. They are not intelligence. They are statistical models that predict the next bit of output. So let's just say they're wrong, is another word to put it. And why is that? Because they have a limited amount of knowledge. They've only been trained on specific things. And the knowledge that they have, even though LLMs do not encode facts or knowledge, but let's just say that anything they know, in quotes, is frozen at the time of training. They cannot respond on anything that's happened after the training has taken place, which means that what they know gets progressively more stale as time passes. Another problem is that they don't have access to your data. So if you're asking them about a collection of data or something you've input into their system, they can only respond based on the prompt and what you have trained them on. And finally, there's a problem I have named commonness bias. It's not exactly the availability heuristic or recency bias or even the Einstellung effect, which is the Einstellung effect is I tend to solve a problem in the way that I'm used to solving other problems. Availability heuristic is I will respond with whatever is more convenient to retrieve. The problem with LLMs is slightly different. I find that they are very much more likely to respond to a difficult query with something that they find easier to respond about. So let's take a real world example. When I was asking an LLM, multiple LLMs actually, to give me code and information for Apache Pulsar, which is a project that supersedes Apache Kafka, because 99.9% of the material you'll find on the internet is based on Apache Kafka. What they would tend to do is they would always return responses about Kafka, even though they didn't apply to Pulsar. And that's what I call the commonness bias, because the most common material they would find to train them on would talk about Kafka instead of Pulsar. The LLMs assumed that when I was asking about that, and because these two were numerically close, that they could respond about Kafka. So that's a very real problem. Any Eurovision fans in the audience? So this is recently retrieved, a screenshot from a model called Claude. How can I tune toast compression level in PostgreSQL? It gives me a very confident answer that I can tune the toast compression level actually in multiple ways, one of which is this: you should do this and that. This is, of course, completely wrong, because this tuning parameter doesn't exist in PostgreSQL. So, as we said, LLMs do not encode facts. They only respond with what is the most likely response to satisfy your query. So how do we deal with that problem? one way we can deal with the problem is retrieval-augmented generation, or RAG. So let's talk a little bit about what RAG is. What is RAG? It's retrieval-augmented generation. It incorporates information retrieval into the cycle of generating a response in the LLM. What does that mean? It addresses the problems we talked about. It reduces wrongness or hallucinations, and it gives the LLM fresh data that it can respond with. So how does it do that? It supplements the information that is not available in the LLM training data, but exists in your database. So, okay, information retrieval. What can we use for information retrieval to feed to the LLM? Survey says, according to the 2025 Stack Overflow developer survey, the most admired and desired database is PostgreSQL for the third year running, and it has quite a lead over other databases, at least from the viewpoint of developers. So what database can we use for AI? The response to the survey for learners was MySQL, with quite a significant lead, which shows us that MySQL is really popular because it has a low barrier to entry, and it's probably more friendly for someone just starting out to code AI applications. However, when you pose the question to professionals working with AI, you see that the response is slightly different and things are reversed. Postgres is the most used database by quite a significant margin, followed by MySQL and so on. So how does retrieval-augmented generation work? So the secret sauce is basically vector embeddings, or otherwise known as word embeddings, which is what we are tokenizing the content, the corpus of material that we're training the that we're going to use for our RAG. We're tokenizing it into words, and we're converting those words into numbers. And these numbers are basically vectors of real numbers. So we are encoding words into vectors, and that's what vector databases are all about. Now, we saw in the previous slides, right, that really people do not use, for AI, right? You would think that you would need to use a specialized vector database. This is not reflected in the survey responses. We see that people are using databases with vector capabilities and not specialized AI databases. So that's a load of hype. That is simply not true, that you need a vector database. So how do you turn your data into vectors? You apply a model that categorizes them by meaning. So it clusters them together. So vectors of words that have meanings that are related are clustered together, as you can see here in Dave Turetsky's wonderful diagram, which is open sourced for his course, and you can find it on GitHub. And this this area of study is called distributional semantics, which is how close are things grouped by meaning. So another important part of retrieval-augmented generation, of course, is indexing, which is converting the text input into vectors by using what is known as an embedding model. So we are creating these embeddings and we're storing them in a database, and we need to create indexes in that database so that we can have fast retrieval. So the next step after indexing, which is the creation of the embeddings, is retrieval, which is basically sending the user query to the database, and you expect the query to fetch the most relevant documents. And by documents, we mean the original material that has been ingested. The final stage is known as augmentation. So augmentation is engineering the prompt based on what has been retrieved from the database. So after you retrieve the original text that was indexed into the database, you feed it into the prompt, and that augments the prompt so that it can give a better and more informed and fresher answer. And the stage of generating the answer is the final stage of RAG, which is generation. So after the LLM has been fed all this data, it just produces a result. Now let's see how we can use pgvector to do RAG in Postgres. So it's an extension. Postgres, it has a very rich ecosystem of extensions that can be used to expand its capabilities. So pgvector is one of them. It adds a new data type called vector, and it stores vectors as a simple column inside the table, as you would expect from a relational database. And now that you have vectors, the good stuff, the embeddings, is inside your database. So it can live close to your data in the same table or an adjacent table that you can join with. And this is great because you can store the original document alongside the embeddings and alongside any other metadata that you would find useful. So how do you use it? Very simply, you create extension pgvector to enable the extension after you've installed the packages. And very simply, you just create table, let's say documents, where the content of the documents is a text column. And then you create an embedding column of type vector with a specific size. Now, what is this size? This size is the dimensions of the vector column. So why do we need this? Because we need this because different models encode and retrieve different dimensions of vectors. So the more vectors that your model can encode or retrieve with, the more accurate probably the retrieval will be. This is not always true, but generally speaking, more dimensions in a vector leads to greater accuracy. So, okay, you've created the vector table. You've now fed the data in. How do you retrieve it? You simply do select content because you want the original input to be retrieved from documents. And then you order by the relevance to your query. So the relevance here is defined as 1 minus embedding. And then there's this weird spaceship operator to compare it to your query. And because we're comparing apples to apples, we're comparing the vectors to something, the other side also needs to be a vector. So this double colon syntax is Postgres shorthand for cast. So we're casting our query that is text, and we are casting it to type vector so we can compare it to our vector embedding. And this expression, 1 minus embedding, spaceship similarity operator to my query, this returns the distance from what has been actually stored. So this is known as the L2 distance, or Euclidean distance, and it tells you how far apart these two points, or in our case, how far apart these two vectors are. So remember the semantic similarity, how close they were in the diagram when we draw the vectors out over 2 dimensions, or multiple dimensions in this case. This is the distance between the two vectors. So how closely related they are. So how closely my query is related to whatever is stored in my column in my database. And you're going to ask, wow, if I have a lot of material that I've used to ingest and generate embeddings in my database, isn't this going to be slow? Because isn't it like searching with an operator like that is trying to find the similarity between phrases? Well, no, because if you remember, we've converted the text to vectors, and we're searching on vectors. And pgvector, the extension, offers indexes to speed up this search and retrieval operation. And we've got 2 types of indexes available. We've got IVF flat indexes and HNSW, which is navigable small world indexes. It's a technique to speed up the retrieval of vectors specifically. So how do you index those vectors? You create index on the table documents that we just created using, let's say, IVF flat, which is a simpler and faster index to create than HNSW. And you specify that you are indexing the column embedding with vector L2 ops, so Euclidean distance operations. So you have to specify that this index, you have to specify what type of comparison this index will be used for. And with lists equals 100 is because IVF flat puts vectors into lists of vectors, and by increasing the number of lists, then you can increase the possibility of retrieval, but that also makes your index bigger and slower to create. So 100 is a good starting point for IVF flat. Now that we've talked about all the technical stuff, let's talk about problem solving. So what is a problem we can solve with Retrieval-Augmented Generation in Postgres? So let's say, and this is a real world problem that I've used this for. Let's say that you have a large legacy code base. Let's say you have someone who has written, you have multiple people who have written code over 10 or 20 years or 30 years for a specific task. Now, this code base is huge, and it encompasses a whole lot of different writing styles, a whole lot of languages that the code is written in. A whole number of people have worked on it over the years. So what if those code experts who have written the code base have left the organization? It's a very real possibility, and it has happened to every one of us, to find code that is no longer maintained by the same person because they have left the organization. Or if they're still in the organization, they may be too busy to answer your questions on the code because they're doing other work now, and because this is code that they worked on 10 years in the past, which makes it equally possible that they have forgotten what they did 10 years ago for the specific thing you're asking them. This is also true, and this has also happened to me. So what is a possible solution for this problem? You can create a RAG system, and that RAG system is what you can ask as your code expert to analyze the pre-existing code. So what you need to do is you need to index the content of your code repositories, and then you create an interface that can query this RAG system. And that's all you need to do, basically. So this interface can be a web chatbot, or you can make it into a Slack bot that you can chat with on your corporate Slack, or any other sort of API that you can query. So let's build one of those solutions and see what a real-world RAG application workflow looks like. So you start by retrieving the code from the repositories, then you generate embeddings on that code, and you put it into your database. Afterwards, after the code has been ingested as embeddings into the database, you enter a natural language query into the interface that you've built. And then I cheat a little bit and I optimize the query based on the nature of the data that we've ingested. And then I use the optimized query to retrieve the code snippets that originally exist in our database. Afterwards, we add the code snippets into the prompt to augment the original natural language query with the relevant code that we've now retrieved from the database. Then this engineered prompt that we've created is sent to an LLM, and the LLM takes care of formulating the response and formatting it in lovely, let's say, Markdown, and displaying it on the query interface, whether it's a web or chat. For bonus points, you want to keep around the conversation history for each interaction. So it becomes like one of those commercial type chatbots that remember what you told them 5 minutes ago because it's part of the same conversation. So first step, retrieve the code from repositories. So you want to do something like, I prefer Python, so I wrote a Python script that clones the repositories. So basically, you import the GitHub library if your repositories are on GitHub, and then you give it your GitHub token that you've assigned for your RAG system. And then it just gets the user for that token, and it loops over the repositories that are accessible to that user. And this way, you can simply just clone them into your local storage one by one. Now, after you've retrieved all of the code locally, you need to put it into a database. And you should prepare a table for this. So let's say you create a table called source embeddings, where you have a repository name, you have a file path for the specific file in that repository. Then you have the content, which is the contents of that file. And then you create two embedding columns. What I've done here is I've created a semantic embedding which I'm going to use. We'll see how. And I've created another column for a code embedding. And you will notice that these have different numbers of dimensions, which means that probably I'm going to be using a different model for each one of those. And then some metadata like created at, which is the timestamp of ingestion, and the commit that the file belongs to. So this is how you can refresh your database contents after the code changes. So you can keep it live as the code changes, and as commits keep rolling into your repository, you can just run a refresh and it will only rescan and create embeddings for the files that have actually changed. And of course, you create a primary key, which is what file it is and which repo it's in. So that's your whole table done now. The next step is you index the repositories. So you create the embeddings in the database for each one of those files in your repositories. And as I said, I'm using in this example a dual indexing strategy, which is both semantic and code embedding. So I'm using a semantic model that extracts natural language-like meaning out of the code, and I have a code embedding that tries to match code snippets to code snippets. Why is that? I want to have the most accuracy for what I'm looking for, and I found that this strategy gives you a good balance between just typing out code and just typing out natural language in your prompt. So what I do in Python is from sentence transformers, which is a wonderful package. I import sentence transformer. From transformers, you import tokenizers and models. And then you define the model. For my semantic model, I've chosen from sentence transformers all mini-LM L6v2. It is a model that I used for extracting the semantic content of the code. Device equals CPU because I didn't have any graphics cards that I could use for this model to perform the extraction of the code into embeddings. And then some details like eager attention implementation. This is the detail that we don't need to get into for this talk. For the code embedding model, I found that Salesforce has created a model called T5 that is very good at finding the relevant files. So you give it its required options as well. And this is how we've initialized our two models that are going to extract the embeddings from the source code. The semantic model is fine. The code model needs code tokenizer. So you just use the code tokenizer that is provided by that Salesforce T5P model.
I think, Jimmy, you froze, at least for me.
Yes, Jimmy, you're frozen.
Okay, it seems like we're having some technical difficulty here, so Jimmy will be shortly back. We're not letting him know right now.
Yeah, let's wait for him. He might have a temporary problem with connection. These things happen during live events. By the way, if you guys have questions, please write in the Q&A tab, and when Jimmy is back, we will ask him these questions. If you have any comments to share, please write them in the chat. And
we can't hear you, Jimmy.
probably is having some connections problems. Um,
Like I can hear Federico, but not Jimmy. I can see Jimmy's slides, but I can't hear Jimmy. So if Jimmy, if you're speaking, we can hear. Oh, we can see what you're doing on the slides, but we can hear you.
I'll just okay.
Oh, now we can hear you. Yes.
So apparently something bugged out when I was having connection trouble. Sorry, let me start resharing slides.
No problem.
Okay, no problem.
Okay, so we were talking about indexing your repositories, and you want to write a Python script that creates the embeddings. So we've been through that. You want to pre-process your code for better embedding quality. So you want to normalize white space. You want to remove comments from the code because you don't want the LLM to return what it reads in the comments. You want it to actually analyze the code that may not any longer match the comments that are above it. And then because string literals are irrelevant, you just replace them with a placeholder like string, and you want to remove consecutive blank lines. This improves the quality of the embeddings. And you can do this with really simple Python code. I've used some regular expressions here to process the text. It's really not hard to do. So now we've generated the embeddings. You want to choose a chunk size. This is an imprecise art. So I've used trial and error to find the chunk size that worked better for these models. For semantic, you want to split the code into overlapping chunks of code. And you do this simply with a function that you define in Python. For code T5 plus, we use smaller chunks because it doesn't have a very large context window for creating the embeddings. And we use a chunk size of 512. So then we need to tokenize the input for the code T5 plus model. We loop over the chunks and we tokenize the chunks. And finally, we generate the embeddings by putting them into an embedding array and then appending the output to the embeddings. After we have all the chunks for that document or that file from our code repository, we average and we normalize the embeddings of all of the chunks so that we can create a final embedding. And this final embedding is what gets stored in our vector column in our database. So we loop over the chunks for the semantic embedding. Then we normalize them, we average them, and we store it into the database with a simple insert statement. So insert into source embeddings, the metadata fields that we want, values, blah, 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 placeholders in Python. On conflict, why do we do this? Because we want to be able to refresh the code in the database from our repository when our repository gets updated with fresh code. So you define an on-conflict clause to do an upsert, and in the case of a conflict, you just update all the new values. Finally, after you've inserted them into the database, you create an index on the source embeddings using IVF-lat is what I've chosen here because it is fast to create the index. And I'm going to use cosine comparison here instead of L2 distance because I've found that it returns more accurate results for this sort of text embedding and data. And then we create another index on the code embedding column, again, using the same strategy. Finally, when I'm querying the database, I cheat, as I said, a little. So I have an LLM that optimizes the natural language prompt that you enter, and then it tries to generate a semantic type query and a code type query that we can use independently to retrieve from those separate columns. So you generate the query embeddings with Python await for making it asynchronous after you've sent the query to the LLM, and it gets those two query strings generated from the LLM. So pgvector expects this type of format. So you generate the query in that format from within Python. And finally, you send the query to the database. So I select the metadata and the content from and the distance from the semantic, the cosine distance. So this is a different spaceship operator with an equal sign in the middle. So this means find the cosine distance between my semantic query and the semantic embedding, and my code query and the semantic and the code embedding, excuse me. And then you rank them with a window function, which is row number, by semantic rank and by code rank. So after I've created the rankings, I select from rankings the top 20 semantic matches from the database and the top 10 code matches from the database. Now, if they score, if the result file that gets retrieved from the database scores highly in both brackets, both code and semantic, they get a boost. And then finally, I send the augmented query to the LLM. And the system prompt reads something like, you're an intelligent code assistant with a heavy focus on Postgres. Below, you will find relevant code patterns from the user's code base and use these patterns to provide accurate contextual responses about the specific database implementation. And then in the instructions, I tell it that it's highly relevant if it ranks highly both in semantic and code structure, so you should prioritize those. So what are sample queries that you can send to an LLM? You can say that for an insurance company, for example, how do we price life insurance? I'll make it really quick. So for another example is what the workflow is for adding a conference attendee to the system. So these are your sample queries. Some tips are, I used Fast API. You can make this into an API tool or a command line tool. By using free embedding models, you can save on costs. versus sending your embeddings to an expensive commercial API for the data indexing step. If your system has multiple repositories, then this can give you a system-wide answer because it can scan multiple repositories. So application side, you can send your augmented prompt to an external LLM, which costs, and you can get like error messages like the server is overloaded. And there's also no guarantee that the model will be the same tomorrow. Or you can run something open source like Ollama, and you can run your LLM yourself, which is best for information security because you keep everything locally. You don't send it to someone else's server, and for cost reasons. But these open source models may not be on par with commercial models. Now, we said the IVF flat stuff versus HNSW. Some caveats is that even when you're retrieving information from your own sources, LLMs can still generate misinformation if they misinterpret the context. And for those open source models, where's the training data? So are they really open source? And always remember this. This is a diagram I've pulled from my book. It's when you're sending someone to someone else's computer, you are bound by their terms of service and privacy policy, as opposed to doing it locally. You can find me very easily on socials. I'm Virus or Jimmy Angelakos on all of those. And here is a discount code for my book, PostgreSQL Mistakes, as a thank you for coming to my talk. Thanks very much.
Thank you, Jimmy, for tuning in. Thank you for attending the conference. And I can see that we have one question from Federico, if you mind answering. So
Sure.
Federico says, in your experience, how important is it to choose the optimal chunk size for performance and for relevant results?
It is significant. I have found in my limited experimentation that it makes a large difference in the quality of the retrieval. So as I said, there's no handbook that tells you exactly what chunk size to use. So you should probably experiment with the specific embedding models that you're using, because the embedding models behave differently depending on the chunk size that you've selected. As I said, like for embedding, I use like a kilobyte of text overlapping kilobytes of text, whereas, if I remember correctly, and for the code embedding, I use like 512 bytes only, because that's what the model could deal with.
Okay, fair enough. I see that we don't have any further questions. So if anyone has any other questions or concerns, feel free to ask them now. Or if not, well, we're going to be tuning into upcoming talks. So thank you very much, Jimmy. It was nice having you in the conference. And I hope you've enjoyed Jimmy's talk as well. Now I invite you to upcoming sessions and this session. And we're stopping the stream in 10 seconds now. So thank you very much, Jimmy. It was nice having you. Yeah.